Welcome, focused learners, to today's explainer. Look, I want you to picture the exam hall. The clock is ticking down, the tension is high, and you're staring at a Cambridge 9618 AS and A-level computer science past paper. Today, we are tearing apart a topic that sounds deceptively, almost laughably simple, but is actually the silent grade killer of the entire syllabus. We are talking about the absolutely critical difference between IEC binary prefixes, your Kibi, Mebi, Gibi, and Tebi, and SI decimal prefixes, your kilo, mega, giga, and tera. Now, this session isn't just a basic vocab lesson. No way. This is about top-tier exam strategy. It's about tailoring your answer to fit the question perfectly, kind of like a master fashion designer where there are absolutely zero loose threads. I want you to imagine two totally different students taking this exam. Let's call them Alex and Sam. Now, Alex overloads the paper with raw, unfiltered computer science facts memorized verbatim from the textbook. Just paragraph after paragraph of data, but zero actual analysis. And then there's Sam. Sam is rushing. Sam sees a calculation, starts to panic, and completely misses the specific requirements hidden in the command word. When the results come back, both of their answers are just bleeding red ink. Why? Because they fell right into the trap. Well, stick with me because by the end of this explainer, you are going to have the exact blueprint to ensure you never make their mistakes.
A senior examiner recently made a massive point in a report stating that most students lose easy marks on binary prefixes. But after we go through this, you absolutely won't be one of them. We're putting on our subject specialist hats today to see exactly what examiners are actually hunting for when they grade your paper. You see, misunderstanding Kibi versus kilo, it really isn't just a minor math error. Actually, scratch that, it's not a math error at all. It's a giant red flag to the examiner that you don't grasp the fundamental architecture of computer memory. When you confidently write down that a kilobyte is 1,024 bytes, the examiner immediately knows you aren't applying the correct IEC standards required by the Cambridge syllabus. You're showing them you don't know your base 2 from your base 10. We are going to decode the exact playbook examiners use, step by step, so you can lock in those easy marks and bump up your grade boundary.
Here's our exact roadmap for today. First, the binary prefix trap. Second, Kibi versus kilo explained. Third, earning method marks. Fourth, top 3 examiner warnings. And finally, the evaluation strategy.
Section 1, the binary prefix trap. Let's get right into the core principles.
Okay, the whole foundation of the Cambridge assessment framework is that it strictly prioritizes analytical depth over superficial breadth. Examiners are testing your logical reasoning across 3 very distinct cognitive domains: knowledge and understanding, application, and analysis. Knowledge is simply knowing the facts, right? Knowing that Kibi is base 2 and kilo is base 10. Application is taking that knowledge and actually using it to convert file sizes. But analysis, well, this is where the top grades live. This requires structured, systematic reasoning. If you get a scenario about a hard drive manufacturer quoting space in terabytes, but the operating system is reading it in Tebi bytes, you can't just define the terms and walk away. You have to explain the discrepancy. Analysis is explaining exactly why a file transfer takes way longer than expected, because the network speed is measured in bits per second, but the file size is measured in Mebi bytes. To nail this, you must decode the command words using the PEEL framework. You make your point, you provide evidence, you add your explanation, and you link it back. PEEL. Master that, and you master the exam. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2, Kibi versus kilo explained. Let's break down base 2 versus base 10.
So, for decades, the computer industry was frankly pretty sloppy. Everyone just treated a kilobyte as 124 bytes. Why? Because 124 is 2 to the power of 10, which is wonderfully conveniently close to an even 1,000. But here's the catch. As our storage grew from tiny kilobytes up to megabytes, then gigabytes, and now massive terabytes, that little 2.4% difference, it compounded into a massive, undeniable discrepancy. Think about it. You go to the store, you buy a 1 terabyte hard drive, which is mathematically base 10. But when you plug it into your base 2 operating system, you only get about 931 GB bytes of usable space. You feel ripped off, right? The syllabus demands absolute precision here. The IEC binary prefixes, Kibi, Mebi, Gibi, Tebi, are strictly base 2. The SI decimal prefixes, kilo, mega, giga, tera, are strictly base 10. Just like in physics or chemistry, kilo always means 1,000. If an exam asks for a calculation using megabytes and you use an even 1 million instead of 1,048,576, you literally throw the marks away.
Now, we all know that under real exam conditions, cognitive fatigue is a very real thing. Your brain gets tired and panic sets in. Having a fail-safe is absolutely crucial. So here is a super quick, actionable memory hack. Create a mnemonic using the first letters of the prefixes, K, M, G, T. You can use something practical like keep making good tracks, or, if you want something a bit more playful to help it stick, how about King Midas got treasure? Whatever works for your brain. But the most important takeaway here is this. The bi in Kili, Mega, Giba, and Tebi literally stands for binary. Kilobinary, megabinary, Giba binary, Teba binary. If you see that bi, you must multiply or divide by 1024. No bi, you use 1,000. Locking this specific order in your head right now is going to save you from careless errors when the pressure is on.
Section 3. Earning Method Marks. Let's look at the procedural framework.
Remember those red pen marks on Alex and Sam's papers we talked about earlier? Well, here is exactly how we transform those into green check marks. To safely secure method marks, you need to follow a very strict procedure. Step 1. Extract from binary representation. You need to explicitly write down the numbers you are pulling from the exam scenario. If the prompt says 4 Gibi bytes, literally write down 4 times 2 to the power of 30 bytes. That single line of ink proves to the examiner that you have the knowledge and understanding. Step 2. Perform calculations. Write out the full equation on the page before you even touch your calculator to solve it. Show the examiner you know that to get from bytes to bits, you have to multiply by 8. Step 3. Draw evidence-based conclusions. This is the link part of our PELL framework. State your final answer clearly and always use the correct units. Look, even if your calculator completely betrays you right at the final second and you write the wrong final digit, documenting your logic this way secures those precious method marks.
And this exact same procedural framework applies perfectly to algorithmic thinking as well. Step-by-step decomposition is essential for coding success on these papers. Step 1. Design your algorithms. Step 2. Implement the solutions. Step 3. Test them thoroughly. Step 4. Evaluate their performance. Whether you are writing pseudocode or evaluating a full system, the examiners are desperately looking for this structured process. Selecting the appropriate data structure and actually showing efficient code implementation earns you marks at every single step of the way. Do not just jump to the final line of code. Show your working and explain your variables. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Top 3 examiner warnings. Let's get into some critical analysis. Okay, welcome to the interactive workshop part of our session. We have pulled the top 3 easiest ways students lose marks straight from the principal examiner reports. Warning 1, students completely forget to check overflow and edge cases in their binary calculations. Think about it. If your algorithm is meant to store a massive Gibi byte value, but you carelessly declare the variable as a 16-bit integer, boom, it's going to overflow. Warning 2, missing boundary conditions. What happens to your code at exactly 0? What happens at the absolute maximum capacity limit? If you don't test it, you lose the mark. And warning 3, writing generic, out-of-context answers. If a paper asks about a 5 megabyte image file being sent over a 10 megabit per second connection, and you don't adjust for that base 2 versus base 10 difference before you calculate the transfer time, well, you've just fallen headfirst into the trap.
Let's really deep dive into what edge cases and boundary conditions actually mean in the context of capacity planning. I want to do a quick challenge. Challenge 2. Find the flaw. Listen to this thought experiment. Imagine a student writes this on their exam. The system can store up to 1,024 Gibi bytes of data. To prevent errors, we just need to make sure the user doesn't upload a file larger than 1,024 Gibi bytes. Okay, where is the flaw in that logic? I'm giving you a virtual 60 seconds. All right, time's up. The flaw is that they completely missed the edge case. What if a user uploads a file that is exactly 1,024 Gibi bytes, but the operating system needs overhead space for file metadata? The whole system crashes. Extreme or limit values in a system will always cause algorithms to fail or data to overflow if they aren't explicitly tested in your tracing tables.
And right here is the absolute loudest warning of all, examiner alert. You must always link every single point to the given scenario. Generic answers earn 0 marks. Let's do challenge 3, speed writing. Let's imagine a scenario where a hospital is backing up life-saving patient records. The command word on the exam is justify. If you just write solid-state drives are fast and use Mebi bytes, you get a big fat 0. Why? Because it's generic. It's not linked to the hospital. A perfect Peel paragraph looks exactly like this. Point. SSDs should be used for the hospital backups. Evidence. The scenario requires immediate retrieval of life-saving records. Explanation. SSDs have no moving parts, which drastically reduces read and write latency compared to magnetic drives. Link. Therefore, the incredibly fast access time ensures doctors can retrieve critical patient data in emergencies without any delay. That, my friends, is how you tailor your answer.
Section 5. The evaluation strategy. When you are asked to evaluate algorithm quality, you are not just describing what the code does, you are comparing it. Comparative analysis requires you to identify similarities and differences. You've got to use comparative connectives in your writing. For example, you should write something like, whereas algorithm A requires O of n time complexity, algorithm B is far more efficient at O of log n. You must evaluate time complexity, space complexity, edge cases, and their direct effect on overall performance. If algorithm A uses fewer megabytes of RAM, well, that's a massive space complexity advantage. But if algorithm B can handle a giant gigabyte data stream without throwing overflow errors because it has better edge case handling, you have to carefully weigh those trade-offs and support every single comparison with solid evidence.
This is what separates the good students from the top-scoring candidates. Top evaluative thinking means you consider multiple solutions, you analyze the trade-offs, you openly acknowledge the limitations, and you justify your final decisions with hard evidence. When you are asked to evaluate whether a specific network can handle a massive terabyte data transfer, don't just calculate the raw transfer time and stop there. Acknowledge the real-world limitations. Talk about network latency, packet loss, protocol overheads. Analyze the specific trade-offs between taking the time to compress the file first versus sending it entirely uncompressed. The final step to exam mastery is drawing precise, logically sound conclusions about relative importance and confidently justifying your programming decisions to the examiner.
Mastering these strategies is the ultimate key to unlocking your true potential in computer science. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Seriously, drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
Before we wrap up, I want to leave you with one final provocative question to really test the new system we built today. Think carefully about everything we just covered, the massive difference between base 2 and base 10, extracting those method marks, handling those tricky edge cases. Here it is. If your algorithm encounters a maximum GB value boundary condition, exactly how will your code prevent an overflow error? Are you relying on exception handling? Are you proactively validating the input size against the strict data type limits before any processing even begins? Think about it. Write out your answer using the perfect Peel framework and apply it directly to your very next past paper. Keep analyzing, keep testing those edge cases, and never ever stop questioning the code. See you next time.